So problem 3 from exam 3 gives you a rod. You should assume it's uniform unless you're told otherwise, although you could always ask, of mass m and length L with a particle. I'm drawing it somewhat bigger than a particle, but a particle of mass 2m attached to its end, and an axle that's left end, and the system is free to rotate about this axle, which points out of the paper towards you. So this can rotate downwards in the gravitational field. You're given a coordinate system to use, x, y, and it's a right-handed coordinate system because x cross y shows your thumb pointing out of the page towards you. So that's the z direction. And you're asked a series of questions about this, starting with where is the center of mass of the system? Well, you should know center of mass is calculated by just adding up each piece of the system, its mass, multiplied by its position, x sub I, divided by the total mass. Okay, and in this case, we have a rod whose center of mass is, hopefully from symmetry, you know, at its center, and it has a mass m. So its x position is L divided by 2. So that's this point. And then you have a mass, a point particle of 2m at a distance L, and overall mass of m plus 2m. All the m's cancel out. So we're left with 2L plus a half, which is, of course, 4 halves plus a half, or 5 halves, times L divided by 1 plus 2, or 3, or 5, 6L, is the position of the center of mass of this system, so it's going to be somewhere here, compared to x equals 0. Part B says, okay, calculate the moment of inertia for this system. Moment of inertia is each piece of the system's mass times, in this case, everything's along the x-axis, so instead of r, it'll be x sub I squared. This is just a little more complicated. The point particle will be easy enough. That's a point mass, mass 2m at a distance L. But how do you handle a rod when it's rotating about one end? Well, you should remember doing this in class. What we actually did originally was the moment of inertia of a rod about its center of mass, and found it's 1/12 ml squared. The reason you can write this down on the exam, rather than try to calculate from scratch, breaking this up into equivalent point particles, etc., is it's given to you on the exam formula sheet, 1/12 ml squared. Give us freedom just to use it. What's not given to you is the moment of inertia about a rod at one end. So if we had done this complete calculation, we could just change the limits of integration from minus L over 2 to plus L over 2 to 0 to L and get that answer. But I'm not expecting you to do that. Instead, what I expect is that you use the parallel axis theorem that says since this axis is parallel to 1 through the center of mass, I can write the moment of inertia about this end as 1/12 ml squared plus the mass of the rod times the distance between these two parallel axes, which is L over 2 quantity squared, which gives us 1/12 plus 1/4 ml squared. Hopefully you can add these, multiply top and bottom by 3 to convert this to 12ths. So 3 plus 1 12ths is 4 12ths, or 1/3 ml squared. So that's the moment of inertia of this rod about its end, but we still have to take into account the point particle. So I total, remember that you sum these things, so you just sum all the pieces of the system. I total is 1/3 ml squared. The moment of inertia of this mass 2m, remember just 2m times its distance squared, so that's 2m times L squared. And so what we have is, again, just add these fractions. So you've got some 6 thirds is 2, 6 plus 1 is 7, or 7/3 ml squared is the moment of inertia of this complete system, rod plus particle, about that axis. Okay, part C says, okay, what's the torque about the axle due to gravity? Okay, so to get the torque, the basic idea is, the definition of torque is R cross F. Now you can do this two ways. You can treat this as one system of rod plus particle, or you can do the torque separately of the rod and of the particle I'm going to do the former, but the solution sheet, written solutions show you both ways. So, but I'm going to do the former because we already have everything we need here. We've calculated the position of the center of mass. Remember, external forces behave as though they act at the center of mass. Okay, and so we can just go ahead and use that information. Okay, and so the force acting at the center of mass, well, that's just going to be the force of gravity, negative 3 mgy hat, because you've got a mass 3m, multiply that by g, and the direction is downward, negative y hat. We've got the r vector. Remember, r is from the axis of rotation to the point where the force acts, and that's what we calculated up here. So r is equal to 5, 6L x hat. Okay, and then just multiply this out. R cross F will be the magnitude of R, which is 5, 6L, times the magnitude of F, which is 3 mg. And you get the direction of the torque from the right-hand rule, which is R cross F. Well, R is in the x direction. Y, oops, I gotta flip my hand, is in the negative y direction. So my thumb points into the paper, and that's the direction of the torque vector. And just multiply out 3 divided by 6 is 1/2, so you have negative 5/2 mg L and z hat. And it might help you to connect this to the rotation that you would see. Remember, a negative z hat rotation means put your thumb in the direction of z, which is pointing down the paper, curl your fingers around, and this would be the sense of rotation, which would correspond to this rotating down for negative z hat. So this is a sensible direction for the torque. Okay. So now we're asked in D, if you release the rod from rest, what's its initial angular acceleration? Well, now we have another expression that relates torque to angular acceleration. Torque equals I alpha. And we can use this in the form alpha equals torque divided by I to calculate the angular acceleration at that moment when this thing is horizontal. This will change as it falls. Whenever it's vertical, there's no angular acceleration because R and F are in the same direction. So it's not a constant acceleration, but at this moment in time, the torque is, we just calculated, in magnitude. Let me just use that, 5/2 mgl. The moment of inertia, we calculated it up above here, is 7/3 ml squared. Now all you have to do is simplify, and you can lose credit if you don't simplify on something like this. Okay, and so the m's cancel, don't have to worry about that. The squared L cancels that factor of L. 5/2 divided by 7/3, well, it's 5 times 3 divided by 2 and 7. So you've got 15/14 G over L. Now let's worry about the direction. Well, the direction of the torque and alpha are in the same direction. So we got that from up here. So this is negative z hat. Will be the direction of the angular acceleration, which again makes sense because the angular velocity will be increasing in the direction down into the paper as it begins to fall. So that's the answer to D. And we have one last part. This one last part says to use energy principles to determine the angular velocity. So when this thing does fall, how fast is it moving? What's its angular speed when it's vertical, completely vertical? Okay. So energy is going to be conserved there. There's no reason for it to lose any energy. So we'll use conservation of energy to answer that question. You'll get into deep, deep trouble if you try to use equations relating alpha to omega, because remember, alpha is not constant, so you can't use any of those simple formula. You'll have some interesting integrals to do if you tried to work it out this way, and I'd be surprised if anyone in the class can do that correctly, although it's possible in principle. So in any case, gravity is going to be a factor, and we'll take that into account with gravitational potential energy, which I'll define to be 0, okay, at y equals 0, at the original position. Okay, and we have E final equals E naught, okay, and what's E naught? E naught equals 0. This thing is at rest with 0 gravitational energy and no kinetic energy. So basically this problem comes down to being able to write E final. E final has both translational and rotational terms. The rotational kinetic energy is 1/2 I omega squared when it's vertical, and well, there's no translational energy, I'm sorry, it has rotational kinetic energy. Everything is rotating, but it has a change in gravitational energy, and that'll be its mass, 3m, g. Remember, everything, the system behaves as though all the mass is at the center of mass, so I want to know what is the change in the height of the center of mass. At the bottom, we were interested in calculating the rotational speed. H center of mass is negative 5,6L. The same thing we found up here, except now the center of mass will have moved from this point, y equals 0, down to a distance 5,6L below 0. Okay, so H center mass is then a negative distance below the x-axis. Okay, so put it all together. Okay, and what do we have? Well, we have this expression equals 0, so we have 1/2 I omega squared equals 3 mg times H center of mass, and we can start solve for omega. So omega equals the square root, okay, multiply both sides by 2 over I, so we have 6 mgh over I. Okay, now we plug in the values for h and I, so we have the square root of 6 mg times, oh, by the way, this is a negative sign, you might have noticed. This is a negative sign too, so that's why those signs will cancel when I plug in a negative for that. Okay, so that's 6 mg times 5,6L divided by the moment of inertia, which we found up here, 7/3 ml squared. Okay, and all you have to do is simplify. M's cancel. This L cancels that squared. We're left with the G over L plus numerical factors. Okay, so omega equals the square root. And what are we left with? Well, I can say this 6 cancels that 6. So 3 times 5 is 15 divided by 7, G over L. Done.